Okay, chapter 26 review. Start with number 7. The chi-square test can only be used on one univariate. Univariate means one variable, categorical, that's good, that's a check, data. Now, this chi-square test is your chi-square test of homogeneity and independence, and those have two variables. All right, it's the goodness of fit test that has one variable. So this is a false problem. All right, number 8, the chi-squared test statistic for testing for independence. So chi-squared test of independence with the two variables when we have a matrix. It's defined by an R by C rows by columns contingency table has rows minus 1 times columns minus 1 degrees of freedom, and that is true. That is a straight up definition. Unlike goodness of fit, that is just categories minus 1. Number 9, the p-value for a chi-squared goodness of fit test, and this is actually a true statement for any of the tests because they follow the chi-squared model. They follow the chi-squared model. Is the area to the left of the calculated chi-squared under the approximate chi-squared curve. So I want to show you a bigger picture of that. And so what we're dealing with is when you are here at 0, then you are closer to the expected. Okay, so the smaller chi-squared, the closer you are to expected. And your p-value is this probability of getting this sample or something more extreme. Extreme on a chi-squared curve is only to the right. Extreme on a chi-squared curve is only to the right since it is only a one-sided curve. All right, next, number 10. The smaller the chi-squared value is, the more proof we have that the populations under study have different proportions represented. Okay, so let's think about that. First of all, I don't like this word proof. That makes me nervous. I would always say the more evidence we have. Okay, so let's think about what smaller chi-squared values mean. The smaller the chi-squared value, the closer the observed is to the expected. Okay, so let's look at what this says here. The p-value the smaller the chi-squared value is, the more evidence we have that the populations under study, so what we're trying to make a claim about, has different proportions represented in the various categories. Okay, and that would be false. And this is the main problem here. The smaller your chi-squared, the closer you are getting to expected. Observed is getting closer to expected. So the more the same proportion represented in the various categories. All right? And we'll go ahead and stop there. So we'll do, oh no, we should finish. Let's just finish this out. 11, as n increases, the width of the confidence interval decreases. Okay, so this is or increases, sorry. The original problem says increases. So this is a total review problem. If you remember from your formula chart that your confidence interval is your statistic plus or minus, and this is your margin of error. All right, and so this is your critical value times the standard deviation. And even if you had a mean standard deviation or a proportion standard deviation, since n is on the bottom, as n goes up, the standard deviation is going down. So if this number is getting smaller, then your margin of error is getting smaller. Think about it. Statistic, margin of error up, margin of error down. If your standard deviation is getting smaller, this margin of error is getting smaller. Therefore, your interval is smaller. As n goes up, your interval gets smaller. It decreases. So that original statement is false. Number 12, as the confidence level increases, as the confidence level, so let's talk about how confident you want to be, the interval increases. Okay, so let's look back at the formula to examine that. So here, our confidence is purely related to the critical value. Okay, so let's look at our critical value here. So for our critical value, if you want to be, say, 95% confident, then your critical value is going to be inverse norm, if you're talking about a proportion problem, of the one tail, 0.025, and that's 1.96. Okay, say you are 90% confident. That's going to be inverse norm of one tail, 0.05, and that would be 1.645. So as you get less confident, you have a smaller critical value. Okay? So therefore the margin of error goes down. The margin of error goes down. Also, think about it this way. On a curve, 95% confidence is wider than 90% confidence. All right? Larger confidence is a bigger interval. All right, so what does that make 12? As the confidence level increases, the interval increases. So that is a true statement. All right, 13. The p-value of any hypothesis test represents the probability of getting, okay, this is definition of p-value, probability of getting the sample result, or something more extreme if the null is true. Okay, we're going to be really picky and say, remember our song, do you remember when we used to sing, the p-value is the probability of getting this sample or something more extreme if the null is true. And if you think about it, getting this sample or something more extreme if the null is true. All right, and finally number 14 is very interesting. I like this problem because it forces you to use the chi-squared chart. So here's what we got. The chi-squared test is performed on a 4x3 contingency table, and the result is a chi-squared value of 17.5. Okay, this right here is telling you the degrees of freedom, and the degrees of freedom would be the rows is 4 and the columns is 3. So 4 minus 1 times columns minus 1. That would be 3 times 2. So that is a degrees of freedom of 6 and a chi-squared value of 17.5. So let's go and look at our chi-squared chart. Here we go. We've got ourselves degrees of freedom 6. So here I am highlighting that row with degrees of freedom 6, and 17.5 is right in here. So that is in between a p-value of 0.01 and 0.005. So let's look at what the choices are. Corresponding probability value is between 0.10 and 0.15, and that is not true. It is between 0.01 and 0.005. Here's your 0.10 and 0.15. Okay? All right, so that is the true-false questions.